this is the molecular formula, C5H10O. Okay, so this is the molecular formula, IR 2950, wave numbers, proton NMR is 3.5, integrates to 4 hydrogens, singlet. And then there was another one that was 0.9, integrates to 6 hydrogens, and it's also a singlet. C13, 64. There was a triplet. Notice there's no integration information on the C13s. These are off resonance decoupling, meaning that the carbons are only allowed to couple with the hydrogens that are directly attached to it. Okay. And then there's one at 4, it's a singlet, and then at 12, it's a quartet. And then these are in units are part per million for both of these. Oops. There we go. Okay, so the first step on all of these things is to determine the degree of unsaturation for these. Because for mass spectrometry, you can find the molecular mass and molecular formula, and you can start to put together some of the structural information, but I didn't give you that information. I gave you the formula, so you need to figure out the degrees of unsaturation. There's a formula in your textbook. I don't use it because I never remember it, but the way I do it is I draw these out in a linear form. So 1, 2, 4, 5.
Just do 2n plus 2.
Yeah, you can do that, yeah. And then when there's nitrogen and oxygen, there's some other stuff in there. So however you want to do it. And then I put in the maximum sites. If the compound were completely saturated, this is what I would have: 3 hydrogens here, 2 here, 2, 2, 2, and then 1 on the oxygen. And then I put in, I have 10 hydrogens, so I started filling them in. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So then I have 2 spots that aren't saturated. And so just keep in mind, each element of unsaturation is going to remove 2 different hydrogens. So the fact that I have 2 spots here, I need to take that divided by 2. That means I have 1 element of unsaturation. And so that pretty much means in this compound that has a carbon, hydrogen, oxygen, that means that I'm either going to have a carbon-carbon double bond, a carbon-oxygen double bond, or a ring. I can't have a carbon-carbon triple bond because that would be 2 elements of unsaturation. Okay? And so now you can look at IR. Like I said, there's no specific order. You can look at what you want to first. Usually I look at IR first because here now you can say, do I have IR structures that correspond to a carbon-carbon double bond or a carbon-oxygen double bond?
Not that you gave us.
And so for this problem, you don't. Okay, the only thing you have is 2950. So that means that you're not going to have these. You don't have anything at what's carbon-carbon double bond is at like 1680, carbonyl 1700. So that means you're not going to have these here. That means you're going to have a ring. Okay? And so now you can figure out, well, what is this 2950 there? What does that correspond to? Okay, so that means I have no carbon-carbon double bonds, so I could have some carbon-hydrogen stretches. Okay, it's possible I could have an alcohol. Do we have a stretch for an OH anywhere? No, so none of this. So this is going to be a sp3 hybridized carbon-hydrogen stretch because we don't have a double bond here. And that's the 2900, right?
Excuse me, just to solidify my thinking, we eliminated the double bonded carbons and the carbon oxygen simply because the IR did not show.
Right. Mm-hmm. Yeah. And then you also don't have any, these would be strong stretches too. Carbon-carbon triple bonds are variable, so sometimes you may not see them. So if you don't see that, you look for you would look for a carbon sp hydrogen stretch too. Okay, or even for this one, you could look for a carbon sp2 hybridized hydrogen stretch for those as just extra confirmation that you don't have those too. Okay. You know you don't have an OH there. So if you don't have an OH, that's a sign that you have an ether right there, right? Because you don't have a carbon-oxygen double bond, so that means you're gonna have some kind of a ether, okay? And so you get that just from IR, okay? Now if I had given you the full spectrum, then you could see if there was any CO stuff going on in the CO region, okay? So now we can look at the proton spectrum. We only have two different types of hydrogen, okay? And so usually when you look at proton, I usually look at proton first rather than carbon just because I'm more comfortable doing proton NMR. I've done it more. So I usually look at proton first, and then you look and see if you have one that's only a slight shift, so small shift and large. Here we don't really see any larges, but we see the small. We look at our proton NMR. What gives us a shift less than 1? Those are alkane. So if you have methyl groups, so the hydrogens on methyl groups typically have shifts of less than 1. And so on this table, the expected would be 0.9 for that, if that carbon would not attach to an electronegative atom. So you get a 0.9. So now you figure, okay, I probably have 2 methyl groups somewhere on this molecule, okay? And they integrate to 6, so that means that you would have 2 equivalent methyl groups. And so then you have one other type of hydrogen, okay? And since there are 4 of them, so now you have 1, 2, so that means you have 3 other carbons. So you have 3 carbons left, but you only have 4 hydrogens. So that means one of the carbons is not going to have any hydrogens on it, okay? And then the other 2 carbons are going to have equivalent hydrogens. And we have a ring, okay? So also, so if we have 2 that are methyls, if it's CH3, that means it can't be in a ring, because otherwise you would need to have 5 bonds to a carbon. So that means that, so 5 minus 2, that means you're going to have a ring with 3 carbons and an oxygen in it. So that means it's going to be we had determined before it's an ether, it means it's a cyclic ether. 3 carbons and an oxygen, because we've already identified 2 methyls. So these are 3 other carbons. And then there's also an ether. So that means, and then we have, now we just have to figure out where do we put the 2 methyls. They need to be equivalent, okay? So if we put them here, if we put 2 methyl groups there, they're equivalent, but then we would be generating 2 different types of protons here instead of 1. Okay, so the only place that those 2 methyls can grow would be here. Okay, and see, this is a carbon with no protons on it, and then this one each has 2. And then again, just double check, make sure you have, the right formula there. 1, 2, 3, 4, 5 carbons, 1 oxygen, 2, 4, 7, 10 hydrogens, the oxygen there, okay? And so everything matches, so we would expect integration for 6 here, and then 2, 4 there. We didn't even have to use the C13, but now we can look, we expect to see a triplet, singlet, and a quartet. So the quartet means a carbon that's attached to 3 hydrogens. Okay, so in this case, this is a carbon attached to 3 hydrogens. So let's go ahead and label these 2. Okay, so I told you to label these. These are in order, but let's just label them 1, 2, 3. So these are this is gonna be carbon 3 here. So there are 3 different types of unique carbons. You have 1 carbon that's a singlet, so that means it's not attached to any hydrogens. So that was 2, so this is carbon 2, and then you have a carbon that's attached to 2 different hydrogens. So it's gonna be a triplet, and so that's our 1. So that's these, and these are equivalent there. And then let me label these protons here. Okay, so this one is, let's say this one is A and this one is B. So these methyls would be B, B, and so then the other ones would be A. And for these, okay, 3.5, so that's in the range for also alkyl hydrogens, but when you have a carbon and 2 hydrogens, so that's on your table. So right underneath the one where you have the methyl group, it has 1.3 is what you would expect, but then for these, but then this carbon is attached to a hydrogen, so you'd expect it to be shifted further downfield.
Carbons attached to a hydrogen.
To
and
2
to the
hydrogens, yeah.
Oxygen.
Right, yeah, so you would expect it to be, because this carbon, this hydrogen here, just from the table, you would expect a value of 1.3.
Okay.
But because this carbon is attached to an oxygen here, it's gonna end up being 3.5.
Okay.
So that would fall down here with the RCH2X.
Yeah, I think I have one of those somewhere
It's
too.
Yeah.
between
Right,
three
yeah,
and
so 3 and 5, yeah.
four. Okay.
So that would fit into that one. And so again, it depends on what table you're using, what your expected is. So if you put an expected, for instance, 1.3, then you would need to explain attached to an oxygen, so it's observed as actually 3.5, or something like that, so. Okay.
So you want explanations? It should have been 1 point, what did you just say?
So this is the part, the explain part. So if you just used a simple table that didn't show this one here, and you may put, okay, expected was 1.3, then you would need to write as a part of your explanation here, this carbon was attached to an electronegative oxygen, so it's shifted.
So, you didn't finish labeling, the other 3 hydrogens are the A's as well?
Yeah, so those are A's also, yeah.
Okay.
And then for the carbons here, you can look at the chart for those. So, so the alkyls, so what was the range from that chart? So one of them was from, so the alkanes are from 0 to 30. And then if the carbon is attached to an oxygen, you would expect it to be, is 55 to 90 or something. So these, we assign these as being 1. Here, also, they're shifted further down the field. And then these were the 3s and the 2s for those, so yeah.
How do you know it's a triplet?
How do you know this one's the triplet?
Yeah.
Because it's attached to 2 hydrogens. And so the N+1 rule, if it's attached, if it's gonna be split by 2, you're gonna see 3 peaks. If there are 3 hydrogens, it's gonna be a quartet. And so keep in mind that splitting for carbon, you're not looking at hydrogens on adjacent carbons, you're looking only at hydrogens attached to the carbon. This is one of those, this is off-resonance decoupling, where all the examples, I think all the examples I gave you guys had splitting on the carbons, right? Yeah, so they have splitting on them, it's the off-resonance decoupling, meaning that you're allowing the spin to couple with hydrogens that are attached.
So the hydrogen, those are singlets because they're only attached to one.
Yeah. Now for the hydrogen spectrum, you're looking at hydrogens are split by non-equivalent hydrogens, but they have to be on adjacent carbons. So this hydrogen, there is no hydrogen on this adjacent carbon, so
Right.
it's a singlet. So actually all of these were singlets
Right.
because there is no hydrogen on an adjacent carbon.
Right.
So if we had a situation like, where we had, like this hydrogen would be a doublet for this hydrogen. So they would integrate for 3 hydrogens and it would be a doublet. This one would integrate for 1 hydrogen, okay? And then you have 3 hydrogens on adjacent, so it would be a quartet. So yeah, So protons are different, they'll couple with hydrogens on adjacent, these don't couple with each other though. So equivalent ones
So just
don't split
each one of
other.
those H on that methyl would couple with that H over there.
Right, right, but not with each other. And like I say, with the carbons, the carbon would couple with these three hydrogens that's directly attached to it. So that's the key thing for those, so. Like I say, I'll put an example for the first problem on the quiz on Blackboard, also, so that those who, and I'll send an announcement for those who aren't in lecture, okay?